There's a galaxy out there, hanging in the depths of space, that holds secrets so strange they defy our understanding. Just 2.5 million light-years away, the Andromeda Galaxy isn't just our cosmic neighbor. It's a treasure chest of mysteries waiting to be cracked open. Picture this, a swirling mass of stars, dust, and dark energy, where the laws of physics sometimes seem to bend, where unexplained lights flicker in the void, and where entire star systems behave in ways that leave scientists scratching their heads. This isn't science fiction, this is real, and today we're diving deep into 25 of the most bizarre, mind-bending phenomena hiding within Andromeda's spiral arms. What makes Andromeda such a hotspot for cosmic oddities? For starters, it's the closest major galaxy to our own Milky Way, giving us a front-row seat to its strange behavior. But it's not just proximity, it's the sheer scale of the unknown. From rogue black holes wandering untethered through space to mysterious radio signals with no clear source, Andromeda is a playground for the unexplained. Some of these phenomena might rewrite what we know about the universe. Others, well, they might just leave us with more questions than answers. And that's the thrill of it, because every strange discovery is a chance to peel back another layer of the cosmos. So why should you care about what's happening in a galaxy so far away? Because Andromeda isn't just some distant speck in the night sky, it's a mirror, reflecting back the wild, untamed forces shaping the entire universe. The same mysteries unfolding there could hold clues about our own galaxy's fate, or even the ultimate destiny of everything we see when we look up, and that's why we're embarking on this journey together. Over the next few minutes, we'll uncover bizarre stellar explosions that shouldn't exist, ghostly structures defying gravity, and celestial objects so strange they don't even have names yet. Strap in, because Andromeda is about to show you just how weird space can really get. The first mystery on our list is one that challenges the very foundations of astrophysics, the Andromeda Paradox. Picture a galaxy spinning so fast that, according to everything we know about gravity, it should tear itself apart. Yet there it is, perfectly intact, defying expectations. This is the puzzle of Andromeda's rotation. Based on the visible matter stars, gas, and dust, scientists calculated how fast the galaxy should spin, but when they measured the actual speed, the numbers didn't add up. Andromeda's outer regions are whirling far faster than they should be, as if some invisible hand is holding it together. This is where dark matter enters the scene. Astronomers believe this mysterious, unseen substance makes up most of the universe's mass, acting like cosmic glue to keep galaxies from flying apart. The problem: we still don't know what dark matter actually is. It doesn't emit, absorb, or reflect light, hence the name, so we can only detect it through its gravitational pull. And in Andromeda, that pull is stronger than expected, especially in its outer reaches. Some theories suggest dark matter forms an enormous, diffuse halo around the galaxy, stretching far beyond its visible edges. Others propose that our understanding of gravity itself might need revising, but here's where it gets even stranger. Recent observations show that Andromeda's rotation isn't just off by a little, it's way off. Some stars are moving so fast that even dark matter models struggle to explain them. Could there be another force at play, or are we missing something fundamental about how galaxies evolve? This paradox isn't unique to Andromeda, it's been seen in other spiral galaxies too. But because Andromeda is so close, it gives us the clearest view of this cosmic oddity. Every new observation peels back another layer, deepening the mystery instead of solving it. What makes this so fascinating isn't just the unanswered questions, it's what they reveal about our place in the universe. If dark matter is real, then most of the cosmos is made of something we can't see. If our laws of gravity are incomplete, then everything we thought we knew needs rethinking. Either way, Andromeda's strange spin is a reminder. the universe is far weirder and far more wonderful than we ever imagined. Floating in the vast emptiness between stars like cosmic phantoms are Andromeda's ghostly hydrogen clouds, gigantic structures of gas drifting alone in space, untethered to any visible galaxy. Some stretch over thousands of light years, vast enough to form entire star systems, yet they linger in eerie isolation. These clouds shouldn't exist under our current models of galactic evolution. Clouds of this size and density typically collapse under gravity, birthing new stars or being absorbed by nearby galaxies, but they just hover, defying expectations. The mystery deepens when you examine their origins. One leading theory suggests they're remnants of galactic collisions, shredded debris flung into intergalactic space during violent mergers. Andromeda's history supports this. We know it's cannibalized smaller galaxies over billions of years, leaving behind a trail of cosmic wreckage. But here's the catch: some of these clouds are too pristine, too undisturbed to fit that scenario. They show no signs of the turbulence you'd expect from a galactic smash-up. Another puzzle is their survival. Space isn't empty, it's filled with ultraviolet radiation and high-energy particles that should rip these fragile hydrogen clouds apart. Yet they persist, some for billions of years. How? Telescopes have detected faint magnetic fields threading through them, acting like invisible armor, but the strength of these fields doesn't fully explain their longevity. Could there be an unseen force shielding them? Or do we need to rethink how gas behaves in the extreme environments of intergalactic space? Perhaps the most baffling aspect is their sheer abundance. Astronomers have mapped dozens of these clouds around Andromeda, far more than theory predicts. Some drift eerily close to the galaxy, as if held in place by some cosmic leash, while others wander the void like lost travelers. Their presence hints at a hidden chapter in galactic evolution, one where gas doesn't always play by the rules. What does this mean for our understanding of the universe? These ghostly clouds might be more than cosmic oddities. They could be clues to an overlooked process, a way for galaxies to exchange material across vast distances. Or they might represent a new class of object, one we're only beginning to recognize. Either way, Andromeda's hydrogen clouds remind us that even the emptiest corners of space are brimming with unanswered questions. Now, let's turn our gaze to one of Andromeda's most dazzling enigmas, the blue variables. These aren't your average stars, they're cosmic divas burning brighter than millions of suns, then dimming without warning as if playing by their own rules. Most stars follow predictable life cycles, but these blue giants defy every model astronomers have. One day, they might shine 50 times brighter than usual. The next, they've faded to near obscurity. The swings in brightness aren't just dramatic, they're chaotic, with no discernible pattern. What makes these stars so baffling is their sheer instability. Normally, massive stars like these, some weighing in at over 100 times the mass of our Sun, live fast and die young, exploding as supernova within a few million years. But blue variables stick around, flickering like cosmic light bulbs with faulty wiring. Some theories suggest they're on the verge of collapse, their cores so turbulent that radiation struggles to escape, causing wild fluctuations in brightness. Others propose they're swallowing nearby companions, their outbursts tied to violent feasts on neighboring stars. Here's where it gets even stranger. In 2012, Hubble spotted a blue variable in Andromeda that brightened abruptly, outshining its usual luminosity by a factor of 10. Then just as suddenly, it faded. No supernova, no explosion, just a stellar temper tantrum lasting mere weeks. Events like this shouldn't happen under standard stellar physics. If a star releases that much energy, it ought to tear itself apart. Yet somehow these stars endure, teasing us with their volatility. The implications ripple far beyond Andromeda. If these stars aren't following the rulebook, what else might we be missing? Could their erratic behavior hint at unknown stellar processes, or even new states of matter lurking in their cores? Every flicker, every surge is a clue, and a reminder that the universe is still writing its own playbook, with stars like these as its most unpredictable characters. Deep within the heart of Andromeda lies a cosmic riddle that defies logic. Not one, but two supermassive black holes locked in a slow gravitational waltz. Most galaxies, including our Milky Way, host a single colossal black hole at their center. Yet when astronomers peered into Andromeda's core, they found an impossible duo, two monstrous voids, each weighing millions of times the mass of our Sun, circling each other like rival kings sharing a throne. How did this happen? The answer lies in Andromeda's violent past. Galaxies grow by consuming their neighbors, and Andromeda is no exception. Billions of years ago, it likely collided with another galaxy, merging their stars, gas, and crucially, their central black holes. Normally, these black holes would eventually spiral together and merge, but here they've stalled, separated by just a few light years, caught in a gravitational standoff. Simulations suggest they've been orbiting each other for tens of millions of years, far longer than expected, as if some unseen force is holding them apart. The implications are staggering. If two supermassive black holes can coexist for this long, it challenges our understanding of how galaxies evolve. Their gravitational dance stirs up the surrounding stars, creating a chaotic region where orbits become unpredictable. Some stars get flung outward at incredible speeds, becoming hypervelocity escapees. Others are ripped apart in dazzling tidal disruption events. Even more bizarre, their presence may explain why Andromeda's core appears unnaturally bright, as friction from their motion heats surrounding gas to extreme temperatures. But the real mystery is what happens next. Will they eventually collide, sending ripples through space-time itself? Or is there some cosmic mechanism keeping them forever at arm's length? The answer could rewrite the story of how galaxies, including our own, are born, live, and die, because one day the Milky Way and Andromeda will meet in a head-on collision. And when they do, our galaxy's black hole might find itself in the same strange dance, turning this distant enigma into a preview of our own cosmic fate. At the heart of most spiral galaxies, you'll find a dense, glowing crowd of ancient stars, a central bulge where countless suns pack tightly together like spectators in a cosmic arena. The Milky Way has one, so does the stunning Whirlpool Galaxy. But when astronomers looked at Andromeda, they faced a puzzle. Where's the bulge? Instead of a bright, star-packed core, Andromeda's center is surprisingly flat, almost like someone took a scoop out of its middle. This missing bulge defies expectations because based on its size and shape, Andromeda should have a prominent one. So why doesn't it? One theory points to a violent past. Imagine a colossal collision billions of years ago where a smaller galaxy plunged straight through Andromeda's center. The gravitational chaos could have scattered the bulge's stars, flattening the core like a hammer striking dough. Computer simulations show such impacts can stretch or even erase bulges, leaving behind a ghostly imprint of the disaster. If true, Andromeda's smooth center might be a cosmic scar, a silent witness to an ancient cataclysm. But there's another twist. Some researchers argue the bulge isn't missing at all. It's just hiding. Infrared observations reveal a faint, elongated structure woven through Andromeda's core, made up of older, cooler stars that don't shine as brightly in visible light. This pseudo-bulge might have formed differently, not through galactic crashes but through slow, steady processes. Gas and stars, tugged by the galaxy's spiral arms, could have gradually migrated inward, building a disk-like core instead of a classic bulge. If so, Andromeda might represent a rare hybrid, a galaxy caught between two evolutionary paths. The implications stretch far beyond Andromeda. Bulges are cosmic fingerprints encoding a galaxy's history. Some are forged in fire, sculpted by mergers. Others grow quietly, shaped by internal tides. Andromeda's ambiguous core challenges our galactic classification system, blurring the line between spiral types. It's a reminder that even the most familiar cosmic structures can harbor surprises, and that sometimes what's missing speaks louder than what's seen. The dark matter halo surrounding Andromeda should be a perfect, symmetrical shroud, an invisible sphere of matter evenly cradling the galaxy. But when researchers mapped its gravitational footprint, they found something shocking. Instead of smooth contours, the halo is lumpy, like a cosmic sponge, with dense pockets of dark matter clumped unpredictably. Some regions pull with twice the expected gravitational force, while others appear strangely empty. This isn't just a minor irregularity, it's a full-blown anomaly that throws our models into chaos. Why does this matter? Because dark matter halos are supposed to be the universe's scaffolding, the hidden framework that shapes how galaxies form and evolve. Computer simulations predict halos should be relatively uniform, their distribution influenced only by the gentle tug of surrounding cosmic structures. Yet Andromeda's halo is anything but uniform. One theory suggests these clumps are remnants of smaller galaxies Andromeda devoured, their dark matter cores lingering like undigested fragments in its gravitational belly. But here's the catch: the clumps are too massive, too densely packed to align with this explanation. Some contain enough dark matter to anchor entire dwarf galaxies, yet they float in isolation, untethered to any visible stars. Even stranger, the clumps aren't randomly scattered. They cluster along an invisible filament, as if strung along a cosmic thread. Could this be evidence of dark matter interacting with itself, something our current models say shouldn't happen? Or does it hint at an entirely new type of dark matter structure, one that forms webs or knots we've never predicted? The implications ripple far beyond Andromeda. If dark matter can clump this way, it might mean the universe's hidden architecture is far more complex than we imagined, with unseen filaments weaving galaxies together in ways we're only beginning to glimpse. What's baffling is how these clumps persist. Dark matter particles, as far as we know, should glide past one another without colliding, making it impossible for them to stick together. Yet Andromeda's halo suggests otherwise. Some physicists speculate there could be multiple types of dark matter, some with weak interactions that allow fleeting bonds. Others wonder if we're seeing the fingerprints of primordial quantum fluctuations, frozen in time from the universe's first moments. Every new observation deepens the mystery. Recent studies using gravitational lensing, where light bends around massive objects, reveal that some clumps warp spacetime more sharply than black holes of comparable mass. Others seem to drift over time, migrating through the halo like ghosts. If dark matter isn't behaving as we expect, it could force us to rewrite the rules of galaxy formation. After all, if the blueprint's wrong, how much else have we misunderstood? Andromeda's lumpy halo isn't just a curiosity, it's a cosmic rebellion. It challenges us to question what we know about the invisible forces shaping the universe. Because if dark matter can defy expectations here in our own galactic backyard, what other surprises are waiting in the void? Scattered around Andromeda like faint fireflies, a swarm of tiny satellite galaxies orbits in stubborn silence, each one a whisper against the cosmos, far dimmer than they should be. These aren't just small galaxies, they're cosmic misfits defying one of astronomy's most trusted rules: the relationship between a galaxy's size and its brightness. According to our models, dwarf galaxies of this mass should blaze with stars, yet these appear almost empty, their light barely a flicker against the void. Astronomers call them ultra-faint dwarfs, but a more fitting name might be ghost galaxies, because their existence haunts our understanding of dark matter. The puzzle starts with their weight. By measuring how these galaxies tug on nearby stars, scientists can estimate their mass, and here's the shocker: they're heavy. Unnaturally so, their gravitational pull suggests they contain huge amounts of matter, but when we look, we see only a sparse sprinkle of stars. Where's the rest of the mass coming from? The leading suspect is dark matter, so much of it that in some of these dwarfs, dark matter outweighs visible matter by 10,000 to 1. That's like finding a shadow that weighs more than a mountain. If true, these galaxies aren't just odd, they're cosmic Rosetta Stones offering clues to dark matter's elusive nature, but even that explanation runs into trouble. Simulations of dark matter behavior predict that halos this dense should attract more gas, birthing more stars than we observe. So why are these galaxies so stingy with starlight? One provocative theory suggests something might be suppressing star formation, perhaps an ancient burst of radiation from Andromeda's core, sterilizing the dwarfs before they could shine. Others propose these galaxies are failed systems, their gas stolen by tidal forces long ago, leaving behind dark matter skeletons. The implications ripple far beyond Andromeda. If these phantom satellites are dominated by dark matter, they could be pristine laboratories for studying it, untouched by the messy collisions that shape larger galaxies. Already, astronomers are using them to test theories like whether dark matter particles can interact with each other or decay over time. But every answer invites new questions. Why do some of these dwarfs orbit in a flat plane like planets around a sun, a pattern almost impossible to explain by chance? And why do a few show no signs of dark matter at all, contradicting the others? The most unsettling possibility, we might be seeing the frayed edges of our cosmic models. If dark matter doesn't behave as predicted in these extreme environments, it could mean our theories need more than tweaks, they might need reinvention. Andromeda's ghostly companions aren't just curiosities, they're mirrors reflecting the gaps in our knowledge, and in their silence they speak volumes. Tucked away in Andromeda's outer reaches, a colossal emptiness yawns wide, a region so barren it defies the galaxy's very nature. This is the Great Andromeda Void, a cosmic desert spanning thousands of light years where stars simply vanish. Galaxies are supposed to be bustling metropolises of matter, their suburbs teeming with at least scattered stars. But here, the stellar population drops to near zero, as if someone carved a hole in the fabric of the galaxy itself. What could create such a void? One leading theory points to an ancient cataclysm, a close encounter with another galaxy whose gravitational might ripped stars away like a tidal wave scouring a shoreline. Computer simulations show such interactions can leave behind tidal tails, streamers of stolen stars, and vast, emptied regions. But there's a problem. The void's edges are too sharp, too clean, unlike the messy aftermath of a galactic collision. It looks less like destruction and more like deliberate erasure. Another possibility involves dark matter. If a dense knot of it lurks in the void's heart, its gravity might repel ordinary matter, pushing gas and stars outward like an invisible force field. Strange as it sounds, we've seen hints of this elsewhere. Dark matter, clumps, that seem to sculpt the cosmos in ways we don't yet understand. Yet even this explanation falters when faced with the void's scale. For dark matter to carve a cavity this large, its distribution would need to be wildly uneven, contradicting our models of how it blankets galaxies, the most unsettling theory. The void might not be empty at all. Radio telescopes have detected faint, diffuse signals from the region, not stars, but something else. Could it be a swarm of rogue planets ejected from their systems and drifting in eternal darkness? Or clouds of ionized gas, too thin to form stars but just dense enough to emit whispers of radiation? If so, the void isn't a true emptiness, it's a realm of ghosts hiding in plain sight. This cosmic blank spot forces us to confront a humbling truth. Galaxies aren't just collections of stars. They're dynamic, ever-changing entities where unseen forces, gravity, dark matter, perhaps even phenomena we've yet to name, sculpt the universe in ways we're only beginning to glimpse. The Great Andromeda Void isn't just a curiosity, it's a challenge, a reminder that even in our own cosmic backyard, the universe reserves the right to surprise us. Among the static and background hum of space, a series of radio bursts from Andromeda crackles with unnerving regularity precise, repeating signals that arrive like clockwork, defying all known cosmic phenomena. These aren't the one-off blips we've detected from distant galaxies. These pulses come back again and again, sometimes in patterns so consistent they've sparked quiet debates. Could we be hearing something more than just natural astrophysics? The mystery begins with their rhythm. Most fast radio bursts, those intense millisecond flashes of energy, are chaotic, unpredictable. But Andromeda's repeating signals follow intervals that border on mathematical. Some recur every 16 days exactly, like a cosmic metronome. Others cycle in sequences that mirror prime numbers, a pattern so odd it's hard to dismiss as coincidence. Natural processes colliding neutron stars, magnetars throwing tantrums, don't operate with this kind of precision. So what does SETI researchers lean in close? While they are careful not to cry aliens, the signal structure is eerily reminiscent of what we might expect from a beacon, a deliberate broadcast. Imagine a civilization synchronizing pulses to mark time or even signal their presence. It's not proof, but it's a tantalizing what if. On the other hand, skeptics point to bizarre stellar objects like pulsars with precession cycles that could mimic artificial timing. Yet no known pulsar behaves this predictably across decades of observation. The real enigma lies in the burst's energy. Their faint barely whispers against the cosmic noise, but their frequencies are laser-focused, concentrated in narrow bands unlike the scattered emissions of natural sources. It's as if something or someone is conserving power, targeting specific wavelengths to cut through the interference of space, perhaps the most chilling possibility. These signals might not be new. Andromeda's light takes 2.5 million years to reach us. If the bursts are artificial, their creators could already be gone, extinct, evolved beyond recognition, or vanished into the void. We'd be hearing echoes of a civilization that flickered out long before Earth's first microbes stirred. But here's the twist: some of these repeating bursts have changed. Mid-cycle, their patterns shift subtly, as if recalibrating. That's not just unusual for natural phenomena, it's unheard of. Whether it's a dying star's death throes or something far stranger, one thing's clear: Andromeda is whispering. And we're just beginning to listen. The outermost stars of Andromeda are doing something they shouldn't, moving in ways that send chills down the spines of astronomers. When scientists measured their light, expecting the predictable redshift patterns that come with a galaxy's steady rotation, they found something bizarre. Instead of a smooth gradient, these stars show erratic shifts, as if tugged by invisible hands. Some race toward us at impossible speeds, while others seem frozen in place, defying the galaxy's gravitational rhythm. This isn't just a quirk, it's a full-blown cosmic mutiny happening right on Andromeda's fringes. Redshift, the stretching of light toward longer, redder wavelengths as objects move away, is one of astronomy's most trusted tools. It's how we measure cosmic distances, track galactic motion, even prove the universe is expanding. But Andromeda's outer stars aren't following the script. Their redshifts scatter like confetti, suggesting chaotic velocities that shouldn't exist in a stable spiral galaxy. One explanation points to dark matter again. Perhaps its halo isn't just lumpy, but lopsided, pulling stars unevenly like a warped magnet. Yet simulations struggle to recreate such extreme distortions without tearing the galaxy apart. Then there's the possibility of an unseen intruder. Could a rogue galaxy or a massive dark matter subhalo have sideswiped Andromeda in the distant past? The gravitational scars of such a collision might still linger, sending stars careening off script. But here's the catch: no visible debris or distorted structures hint at this catastrophe. If an impact occurred, it left no trace except these rebellious stars, a perfect crime, with only redshift as the smoking gun, the most tantalizing theory. Andromeda might be feeding, Some of the fastest-moving stars align with streams of cosmic debris remnants of smaller galaxies it's currently consuming. Like stones flung from a slingshot, these stars could be the survivors of shredded satellites, now orbiting with reckless momentum. If true, we're witnessing a galactic meal in progress, with redshift as our window into the chaos of celestial digestion. But the riddle deepens. A handful of stars show negative redshifts they're barreling toward us against the flow of the galaxy's spin. These could be hypervelocity escapees flung outward by gravitational slingshots near Andromeda's twin black holes. Or perhaps they're intergalactic interlopers stolen from another galaxy and hurled our way by cosmic chance. Whatever their origin, their motion hints at forces we've yet to map, a hidden interplay of gravity and chaos sculpting the galaxy's edge. The implications stretch far beyond Andromeda. If redshift, our gold standard for measuring cosmic motion, can't always be trusted, what does that mean for our maps of the universe? Could similar anomalies lurk in other galaxies, quietly appending our assumptions? Every erratic star in Andromeda's outskirts is a reminder. The cosmos loves to break its own rules, and we've only just begun to read between the lines. Nestled within Andromeda's halo, scattered like cosmic fossils, lie star clusters so ancient they carry the chemical fingerprint of the early universe. These aren't just old, they're pristine, with metal content so low they defy modern stellar expectations. While most stars today are enriched with heavy elements from generations of supernova, these clusters contain less than 1% of the metals found in our Sun, as if frozen in time shortly after the Big Bang. What makes them so peculiar isn't just their age, it's their isolation. Metal-poor stars typically exist in the chaotic hearts of galaxies where ancient populations mingle. But Andromeda's clusters float far out in its halo, untouched by later waves of star formation. One theory suggests they're survivors from Andromeda's building blocks, the original small galaxies that merged to form its current structure. Imagine cosmic time capsules preserving the raw materials of galaxy formation before pollution from dying stars altered their chemistry. Yet there's a twist. Some of these clusters exhibit odd dynamical properties. Their stars orbit erratically, as if the clusters themselves were traumatized by a violent past. Detailed spectroscopy reveals tidal tails, subtle streams of stars being stripped away, hinting at brutal gravitational encounters. This raises a chilling possibility. These clusters might not be primordial at all, but the shattered remains of even older systems, torn apart during Andromeda's aggressive growth. Their metal poverty could then stem from being recycled material stars reborn from gas that never mixed with heavier elements. The implications ripple through cosmology. If these clusters are truly primordial, they could hold clues about the universe's first star's mythical population, Roman III stars thought to be hundreds of times more massive than our Sun. Their supernova would have seeded the cosmos with its first heavy elements, yet we've never directly observed one. Andromeda's metal-poor clusters might be their descendants, offering our best chance to study this elusive generation. Alternatively, if they're shredded relics, their survival challenges our models of galactic cannibalism. Typically, mergers destroy such fragile systems. That they endure suggests dark matter might be cocooning them, perhaps in miniature subhalos we can't yet detect. Either way, these clusters aren't just celestial oddities, they're windows into the universe's most formative eras. Every photon we capture from them carries whispers from a time before metals, before complexity, when the cosmos was young and galaxies were just learning to dance. Buried within Andromeda's spiral arms, an invisible storm rages, a sudden surge of X-rays blazing from points where no light should exist. Over just a few years, astronomers watched in disbelief as the number of ultra-luminous X-ray sources in Andromeda nearly doubled, marking the most dramatic spike ever recorded in a galaxy of its size. These aren't just cosmic flashbulbs going off at random. Each one is an X-ray binary system, a deadly dance between a normal star and something far darker, a black hole or neutron star slowly devouring its companion alive. What makes this surge so unsettling is the scale. Normally, X-ray binaries form over millennia as massive stars collapse into compact remnants, then gradually pull material from neighboring stars. But in Andromeda, dozens appeared almost simultaneously, as if the galaxy flipped a hidden switch. Some of these systems shine with the power of 1,000,000 suns, their X-ray emissions so intense they outshine entire star clusters. The leading theory involves a recent wave of star formation, perhaps triggered by a collision with a dwarf galaxy that birthed countless massive stars, many already destined to become black holes or neutron stars. But here's the problem: even that can't fully explain the numbers. The real enigma lies in their behavior. Typical X-ray binaries flicker as their monstrous partners feed in fits and starts, but Andromeda's new crop burns unnaturally steady, as if operating on a cosmic assembly line. One system, dubbed XP32, pulses with near-perfect regularity every 8 hours, its neutron star slurping up plasma like clockwork. Others show bizarre spectral lines, hinting at elements like titanium and chromium swirling in their accretion disks, materials rarely seen in such concentrations. It's as if something is supercharging these systems, pushing them beyond their natural limits. Then there's the black hole paradox. Several of these X-ray sources appear to host black holes between 50 and 100 solar masses, putting them squarely in the mass gap between stellar black holes and supermassive giants. According to our models, black holes this size shouldn't form from collapsing stars, yet here they are, gulping down matter with terrifying efficiency. Could Andromeda possess a unique pathway for creating midweight monsters? Or are we witnessing the aftermath of smaller black holes merging in dense stellar environments? The implications ripple beyond Andromeda. If X-ray binaries can surge like this, it suggests entire galaxies might have dormant beast modes, periods where their dead stars awaken en masse to reshape the cosmic landscape. For planets orbiting nearby stars, the consequences would be apocalyptic. The intense radiation from just one of these systems could sterilize worlds light years away. And if such surges are common, it might mean the universe is far more volatile than we imagined, with galaxies periodically erupting in violent electromagnetic tantrums. Perhaps the most haunting question is what triggered this event, and whether it's a preview of our Milky Way's future. When our galaxy collides with Andromeda in 4 billion years, could a similar surge ignite here? For now, Andromeda's X-ray binaries keep their secrets, burning like forbidden signal flares in the dark, a reminder that even the quietest galaxies can turn feral without warning. Stretching across Andromeda's sweeping spiral arms, tight clusters of stars and gas coil like cosmic knots, dense, glowing regions where the galaxy's graceful curves twist into chaotic tangles. These aren't just random clumps of matter. Some shine with the ferocity of newborn stars, while others radiate energies that defy explanation. At first glance, they resemble stellar nurseries, the kind we see in our own Milky Way, where collapsing gas clouds ignite fresh generations of suns. But Andromeda's knots tell a far stranger story, one that challenges what we know about how galaxies build their arms. Take the most prominent knot, nicknamed the Anvil by astronomers. Packed into a region just a few hundred light-years wide, it hosts thousands of stars so young they're still swaddled in the gas that birthed them. Yet nestled among them are bizarre, ultra-bright X-ray sources, objects typically found near black holes or neutron stars. This shouldn't happen. Stellar nurseries are supposed to be pristine, dominated by infant stars, not riddled with the remnants of dead ones. One theory suggests these knots are galactic recycling centers, where supernova explosions from an earlier generation of stars compress nearby gas, triggering a new wave of star formation even as the old remains linger. Then there's the enigma of their motion. While most of Andromeda's spiral arms rotate with smooth, predictable grace, the knots wobble erratically, as if tethered by invisible threads. Some drift ahead of the arm's rotation, others lag behind, creating a snarl in the galaxy's otherwise fluid dynamics. Computer simulations struggle to replicate this behavior unless dark matter is involved specifically. Dense pockets of it clustered around the knots, adding gravitational weight that tugs them out of sync. If true, these structures might be more than just star factories. They could be dark matter anchors stitching the spiral arms together from within. The most perplexing knots, though, emit almost no visible light at all. Instead, they glow fiercely in infrared and radio wavelengths, hinting at vast reservoirs of cold dust and molecular gases. These dark knots might be stellar nurseries in their earliest stages, so shrouded in dust that not even the fiercest young stars can pierce through. Or they could be something entirely different: failed star factories where the gas never quite ignited, frozen in a state of near collapse. The presence of exotic molecules like cyanopolyeins, long carbon chains usually found in deep space, suggests chemical processes here are unlike anything seen in our own galaxy. What's at stake isn't just understanding these knots, but unraveling the very blueprint of spiral galaxies. Are they fleeting features destined to dissolve as stars disperse? Or do they seed long-lived structures, influencing how arms evolve over billions of years? Every observation peels back another layer, revealing a universe where chaos and order dance in ways we're only beginning to map. Andromeda's knotted arms aren't just quirks, they're cosmic puzzles waiting to be untangled. One of Andromeda's most baffling vanishing acts isn't happening in the depths of its halo or the chaos of its core. It's unfolding right in the heart of its star-filled disk. Over the past decade, astronomers have watched in real time as dark, ribbon-like dust lanes, once prominent features weaving through the galaxy's spiral arms, have begun to fade, some disappearing entirely. These aren't just subtle changes. In certain regions, thick bands of cosmic dust that blocked starlight for millennia have thinned to near transparency, as if someone slowly turned up a dimmer switch across entire sections of the galaxy. The first clues came from infrared surveys. Dust absorbs visible light but glows warmly in infrared, so when telescopes like Herschel and Spitzer scanned Andromeda, they expected to see the usual intricate lacework of dusty filaments. Instead, they found gaps, patches where the dust signature had weakened dramatically. Follow-up observations revealed something even stranger: the vanishing wasn't uniform. Some dust lanes eroded from the inside out, like ink dissolving in water, while others fractured into disjointed clumps before dissipating. In one notable case, a dust band over 500 light-years wide simply unraveled over a span of just 20 years, a blink of an eye in cosmic terms. What could erase dust on such a scale? One leading suspect is Andromeda's own stars. Massive stars don't just shine, they rage, producing fierce stellar winds that blast outward at millions of miles per hour. When these winds slam into nearby dust clouds, they can vaporize solid particles, breaking them down atom by atom. In regions with recent bursts of star formation, like the galaxy's active spiral arms, this might explain the thinning. But there's a problem. Some of the vanishing dust bands lie in quieter neighborhoods far from any stellar hurricanes. That's where darker forces come into play. Some researchers point to Andromeda's supermassive black hole, which, despite its current quiet state, might have belched out bursts of radiation in the not-so-distant past. High-energy photons from such an eruption could have swept through the disk, charging dust grains until they repelled each other, disrupting their delicate structures. Others speculate about unseen dwarf galaxies or dark matter subhalos passing through Andromeda's disk, their gravitational tug stirring the dust like a spoon in coffee, dispersing it too thinly to detect. Then there's the most unsettling possibility. We might be witnessing a natural life cycle of galactic dust that no one predicted. dust isn't eternal. It forms in the atmospheres of aging stars and the remnants of supernova, then clumps together over eons. But perhaps there's also an unseen process that dismantles it, some interstellar chemistry or quantum effect that unbinds dust particles when conditions are just right. If so, Andromeda isn't breaking the rules, it's revealing rules we never knew existed. The stakes are higher than they seem. Dust might seem like a cosmic afterthought, but it's the raw material for future stars and planets. If it's vanishing faster than it's replenished, entire regions of Andromeda could one day become sterile, unable to birth new solar systems. Worse yet, we have no idea if this is unique to Andromeda or happening across the universe, hidden by distance. Every fading dust band is a silent alarm, one we're only now learning to hear. Streaking through the void like cosmic bullets, a handful of stars defy Andromeda's gravitational grasp, racing outward at speeds so blistering they could cross the entire Milky Way in just 50 million years. These aren't just fast-moving stars, they're hypervelocity runaways, objects hurled from their birthplace with enough force to escape their galaxy forever. The most extreme of them clock in at over 800 kilometers per second, roughly 1/6 the speed of light, leaving even the fastest objects in our own galaxy in the dust. The prime suspect behind this stellar catapult, Andromeda's twin supermassive black holes. When stars wander too close to these gravitational monsters, the tidal forces can rip them apart. But sometimes, in a cruel twist of physics, a star survives the encounter. Instead of being devoured, it's flung outward in a gravitational slingshot, like a stone from a trebuchet. The math is terrifyingly elegant. As the star approaches the black hole duo, one absorbs its momentum while the other flings it away, their combined gravity acting as a natural particle accelerator. The result, a star ejected fast enough to cross intergalactic space, destined to drift alone through the cosmic dark. Yet not all hypervelocity stars fit this neat explanation. A few curveballs linger in the data. Some runaways lack the chemical fingerprints of stars born near Andromeda's core, where black holes dominate. Instead, their composition matches the galaxy's outer disks, suggesting a different launch mechanism. Perhaps a supernova explosion in a binary system, where one star detonates with such force it sends its partner careening into the void. Others move in loose clusters, implying they might not be solo escapees but survivors of entire star clusters torn apart by tidal forces. The most puzzling cases don't even point back to Andromeda. Their trajectories suggest origins outside the galaxy entirely, as if they were intergalactic travelers captured briefly by Andromeda's gravity before being flung onward. Could these stars be rogue nomads ejected from galaxies millions of light years away? Or might they hint at an even wilder possibility, that some hypervelocity stars aren't propelled by black holes or supernova, but by encounters with dark matter structures we've yet to map? What's certain is that these runaways are more than just celestial oddities. They're forensic tools. By tracing their paths backward, astronomers can reconstruct hidden dynamics within Andromeda, the gravitational fingerprints of its black holes, the density of its dark matter halo, even long-forgotten collisions with dwarf galaxies. Each hypervelocity star is a messenger carrying encoded secrets about the forces that shaped it. And as they streak across the cosmos, they remind us that even in a galaxy of billions, a single star's flight can illuminate the universe's darkest corners. Tucked away in the shadowy reaches of Andromeda, mysterious beacons of pure energy pulse with a ferocity that defies explanation, localized gamma-ray hotspots burning brighter than anything else in the galaxy. These aren't the diffuse glows we see from supernova remnants or pulsars. These are pinpricks of raw power, each packing enough energy to outshine 1,000 suns, yet concentrated into regions no larger than our solar system. And what's fueling them? That's where the plot twists into the realm of cosmic whodunits. One leading suspect is dark matter, specifically the mind-bending possibility that these hotspots could be the grave sites where dark matter particles annihilate each other. Here's how the theory goes. If dark matter is made of weakly interacting massive particles, WIMP, then when two of them collide, they might obliterate each other in bursts of gamma rays. Andromeda, with its massive dark matter halo, could be the perfect hunting ground for such events. The hotspots align eerily with predicted dark matter density peaks, as if someone mapped the invisible scaffolding of the galaxy using gamma-ray flares. But there's a catch. If this is dark matter's calling card, the signal is far stronger than any model predicts. It's like finding a candle where we expected a lightning bolt. Something's off in the math. Then there's the astrophysical angle. Some of these hotspots coincide with known extreme objects, supermassive black holes, magnetars, or the remnants of ancient stellar collisions. Take the most infamous one, dubbed Andromeda's furnace. Nestled near a globular cluster, it flickers unpredictably, sometimes flaring to 10 times its usual brightness in hours. That volatility screams of chaotic accretion. Perhaps a black hole shredding a star, or a neutron star's magnetic field snapping like a cosmic rubber band. But even these explanations crumble under scrutiny. The energy spectra don't match known sources, and the timing of the flares follows no discernible pattern. It's as if the universe invented a new way to generate gamma rays and forgot to tell us the recipe. The most unsettling hotspots, though, are the ones with no visible counterparts at all. No black holes, no star clusters, just empty space suddenly erupting in gamma rays. One theory suggests these could be dark pulsars, neutron stars so old their radio emissions have faded to nothing, leaving only gamma-ray death throes as they spin down. Others propose their evidence of primordial black holes, hypothetical relics from the Big Bang, evaporating in bursts of Hawking radiation. But perhaps the wildest idea is that we're seeing the aftermath of quantum singularities, microscopic black holes left over from the early universe, colliding like subatomic pinballs and detonating in flashes of pure energy. Whatever their origin, these gamma-ray hotspots are more than just cosmic curiosities. They're probes into the most extreme physics imaginable. If dark matter is truly behind them, we're glimpsing its decay in real time, a process that could rewrite particle physics. If they're astrophysical, they might represent a new class of object, one that operates by rules we've yet to decipher. And if there's something else entirely, well, that's the thrill of Andromeda. Just when we think we've mapped its secrets, it lights up the dark with questions we didn't even know to ask. Stretching over hundreds of thousands of light years, like celestial brushstrokes against the void, Andromeda's tidal tales tell a story of violence on an unimaginable scale. These vast rivers of stars, some glowing blue with youthful energy, others dulled by age, aren't just random debris. They're the shredded remains of smaller galaxies torn apart by Andromeda's gravity, scattered across the cosmos in a trail of cosmic breadcrumbs. But here's the twist. These tidal tales aren't behaving like they should. Instead of symmetrical streamers curling gracefully around Andromeda's edges, they twist and kink in bizarre, lopsided formations, as if the galaxy itself forgot the rules of demolition. Take the most prominent tail, dubbed the Serpent by astronomers. It arcs sharply to Andromeda's northeast, packed with stars moving in near-perfect unison, like a school of fish fleeing a predator. Yet on the opposite side of the galaxy, its counterpart, the Scorch, is patchy and fragmented, its stars scattered in erratic clumps rather than a smooth flow. This asymmetry shouldn't exist. When galaxies collide, tidal forces should pull material equally in both directions, like stretching taffy from both ends. So why is one side pristine while the other looks like it's been put through a cosmic blender? One clue lies in the tail's chemistry. Spectroscopic analysis reveals the Serpent is rich in metals elements forged in the hearts of stars, while the Scorch is oddly primitive, its stars containing barely a trace of heavy elements. This suggests the tails didn't form from a single galactic meal, but from multiple victims swallowed at different times. Andromeda might have first consumed a metal-rich dwarf galaxy, stretching its stars into the Serpent, then later snacked on a poorer, gas-dominated system, leaving the Scorch as its messier second course. But the plot thickens. Some sections of these tails aren't just uneven, they're moving backward. Stars in the Scorch's western segment actually orbit counter to the galaxy's spin, as if yanked by an unseen hand. Simulations point to dark matter again. A dense knot in Andromeda's halo could be warping the tidal flow, bending the tail like a river around a boulder. Yet even this explanation falters when faced with the sheer scale of the disruption. The forces required would imply dark matter clumps far more massive than predicted, or worse, that our models of galactic digestion are missing something fundamental. Then there's the eerie silence of the missing dwarfs. If these tales are the aftermath of galactic feasting, where are the corpses? Astronomers have scoured Andromeda's neighborhood for the surviving cores of the devoured galaxies, but the search keeps coming up empty. One provocative theory suggests the victims didn't come from outside at all. They might have been born within Andromeda itself. Galactic disks can sometimes fracture under their own gravity, spawning star clusters so dense they mimic small galaxies. When these homegrown dwarfs stray too close to the galactic center, they're torn apart, their stars flung into tidal tails without any external culprit. The stakes of this mystery ripple far beyond Andromeda. Tidal tails are cosmic forensic evidence. They encode the history of galactic collisions, the density of dark matter, even the shape of spacetime itself. If we can't read them correctly, our entire understanding of galaxy evolution might be skewed. Worse yet, Andromeda's twisted tails could be a preview of our own fate. When the Milky Way collides with Andromeda in 4 billion years, the same forces now sculpting these starry streams will reshape our night sky. Will our galaxy's stars one day form strange, asymmetrical tails too? Only by decoding Andromeda's past can we predict our own cosmic future. Deep within Andromeda's core, astronomers have detected ghostly whispers of a sleeping giant, faint, quasar-like emissions pulsing from the galaxy's heart long after its supermassive black hole should have gone quiet. These aren't the brilliant beacons we associate with active galactic nuclei. They're pale echoes, flickering at just 1,000th the luminosity of a true quasar. Yet their very existence poses a startling question. Is Andromeda's central black hole stirring from its slumber? For decades, we assumed Andromeda's core was dormant. Unlike the voracious black holes powering distant quasars, which shine brighter than entire galaxies as they devour matter, Andromeda's central monster appeared content to rest, its accretion disk running on near empty. But in 2019, the Hubble Space Telescope spotted something odd: periodic flares of ultraviolet light dancing around the black hole, followed months later by delayed X-ray bursts. This staggered emission pattern mirrors the behavior of active quasars, just scaled down to a cosmic whisper. The most compelling explanation involves a light echo radiation from a past feeding frenzy that's only now reaching us. Imagine the black hole gorged on a star or gas cloud centuries ago, creating a short-lived quasar flash. While the initial blast faded long ago, its light bounced off dust clouds hundreds of light years away, creating delayed reflections we're just now detecting. If true, we're witnessing ancient fireworks through a celestial hall of mirrors, but there's a darker possibility: the black hole might be waking up. Recent radio observations reveal a slender jet of particles, feeble compared to the relativistic spears fired by active galaxies, but unmistakably present. This suggests the black hole's engine is sputtering back to life, perhaps fueled by fresh gas from a recently disrupted star or an unlucky gas cloud straying too close. The timing couldn't be more ironic. Just as we've confirmed the Milky Way's black hole occasionally snacks on asteroids and comets, we find Andromeda's might be setting the table for a more substantial meal. The implications are cosmic. If supermassive black holes cycle between dormancy and activity over millennia, entire galaxies could experience eras of radical transformation. A fully awakened black hole in Andromeda would flood its core with radiation, potentially sterilizing nearby star systems while simultaneously triggering new star formation in compressed gas at its periphery. For civilizations like ours, it would rewrite the night sky, a once familiar galaxy suddenly blazing with alien light. What makes these echoes so haunting is their unpredictability. Unlike the clockwork pulses of a neutron star or the predictable fade of a supernova, Andromeda's quasar remnants flicker without pattern, as if teasing us with fragments of a language we don't yet understand. Every flash could be the last or the first hint of a coming storm. One thing's certain, we're watching history unfold in real time as a sleeping giant rolls over in its cosmic bed. Buried within the glow of Andromeda's starlight lies an infrared anomaly so glaring it's forced astronomers to rethink how galaxies radiate heat. When telescopes like Spitzer and Herschel mapped the galaxy's thermal emissions, they expected to see the usual blend of warm dust and cooler gas typical of spiral galaxies. Instead, they found a surging excess of infrared wavelengths, more than double what standard models predicted. This invisible ghost light permeates Andromeda's spiral arms, clustering in peculiar patches where no visible star formation or known dust structures exist. The leading theory points to hidden stellar nurseries, regions where newborn stars are shrouded so thickly in dust that not even ultraviolet radiation escapes. Their heat would seep out as infrared, explaining the excess, but detailed surveys reveal a mismatch. The infrared hotspots don't align with areas where gas densities are high enough to birth stars. It's as if Andromeda is hiding entire generations of stars in plain sight, their presence betrayed only by the warmth they leave behind. Then there's the dust itself. Galactic dust typically consists of silicate and carbon grains, which absorb and re-emit light predictably. Yet Andromeda's infrared signature suggests something stranger, either an overabundance of microscopic diamonds which glow uniquely in mid-infrared or porous, fluffy dust particles with bizarre thermal properties. Lab experiments show these exotic grains could explain the excess, but their origins are a mystery. Did they condense in the atmospheres of dying carbon-rich stars? Or were they forged in supernova shocks, their structures twisted by violent turbulence? The most radical explanation, cold dark matter, might be playing a role. While dark matter doesn't emit light, some theories propose it could decay into weakly interacting particles that nudge dust grains, causing faint heating. If true, Andromeda's infrared excess could be the first indirect evidence of dark matter's quantum whisper, a heat signature from the universe's most elusive substance. But the plot twists further. Some of the brightest infrared patches coincide with regions where stars are scarce but X-ray sources abound, hinting at unseen black holes or neutron stars warming their surroundings. Others align eerily with the galaxy's faintest tidal streams, as if collisions with dwarf galaxies left behind not just stars but invisible thermal scars. What makes this enigma so critical is its universality. If Andromeda, our closest galactic mirror, harbors unexplained infrared emissions, how many other galaxies might be hiding similar excesses? The answer could reshape how we calculate galactic energy budgets, star formation rates, even the lifespan of dust across cosmic time. For now, Andromeda's ghostly glow remains a thermal fingerprint without a hand, a reminder that light, in all its forms, still holds secrets waiting to be decoded. Among the orderly swirl of Andromeda's billions of stars, a rebellious faction moves to its own rhythm, stars that spin backward, defying the galaxy's rotation like salmon swimming upstream. These aren't just slightly tilted orbits, they're full-blown counter-revolutions, with some stars hurtling around the galactic center in the exact opposite direction of their neighbors. This cosmic mutiny shouldn't happen naturally in an isolated spiral galaxy. like a perfectly stirred cup of coffee suddenly having droplets spin the wrong way. It hints at something far more violent in Andromeda's past, a history written in the trajectories of these rogue stars. The most compelling explanation: galactic cannibalism. When Andromeda consumed smaller galaxies over billions of years, it didn't just absorb their stars, it inherited their momentum. Imagine two whirlpools colliding in water. Their opposing spins create chaotic eddies that linger long after the merger. That's likely what happened here. A dwarf galaxy orbiting in the opposite direction was torn apart by Andromeda's gravity. Its stars scattered into this new backward orbit. The smoking gun lies in these stars' chemical fingerprints. Many contain lower metal content than Andromeda's native population, matching the primitive compositions typical of smaller, ancient galaxies. But the plot thickens. Not all counter-rotating stars are outsiders. Some appear to be homegrown rebels. In Andromeda's central bulge, astronomers have found populations of backward-orbiting stars with chemistry identical to the galaxy's main disk. This suggests a different, even more dramatic origin: gravitational mayhem caused by Andromeda's twin supermassive black holes. When stars pass too close to these monstrous duos, they can be violently redirected like billiard balls struck at odd angles. Some might flip orbits entirely, joining the counter-rotating ranks through sheer gravitational bad luck. The real shock came when researchers mapped these backward stars in 3D. Instead of being randomly scattered, they cluster in distinct streams, ghostly ribbons winding through Andromeda that trace the exact paths of ancient collisions. One particularly dense stream, nicknamed the Contrarion's ribbon, forms a near-perfect ring rotating backward at 700 kilometers per second. Its stars are so synchronized that they must have originated from a single, catastrophic disruption. Perhaps a globular cluster that strayed too close to Andromeda's core and was unraveled into this cosmic Mobius strip. What makes these stellar rebels so valuable is what they reveal about dark matter. Their orbits act as cosmic probes, mapping the gravitational field in ways visible matter can't. Some backward stars accelerate unexpectedly at certain distances from the core, suggesting they're responding to invisible dark matter substructures, perhaps the remnants of the very galaxies they once belonged to. Others follow paths so contorted they imply Andromeda's dark matter halo is lopsided, still unsettled from its last major meal. This celestial rebellion isn't just ancient history, it's ongoing. New observations show young, blue counter-rotating stars forming in gas clouds that somehow retained opposite angular momentum during past mergers. Like cosmic whiplash, these newborn stars carry the echoes of violence that occurred billions of years before their birth. They're proof that galaxies don't just collide and move on, they digest their victims slowly, with the aftermath visible for cosmic epochs. For astronomers, these backward stars are more than curiosities, they're forensic evidence. By studying their motions, we're essentially watching Andromeda's home movies of its most violent encounters, frame by frame. Each contrary orbit is a time-stamped record of when and how Andromeda grew, revealing chapters of galactic evolution we could never learn from our own Milky Way's more sedate history. And as we discover more of these stellar anarchists, one truth becomes clear. In the grand dance of galaxies, sometimes the most revealing steps are the ones that go against the flow. Globular clusters should be the ancient guardians of Andromeda, dense, glittering balls of stars that formed alongside the galaxy itself, each harboring hundreds of thousands of suns packed into a space smaller than our solar system. The Milky Way boasts at least 150 of these cosmic fossils. Given Andromeda's larger size, astronomers expected it to host even more, perhaps 200 or 300. Yet when they counted, the numbers came up shockingly short. Andromeda has barely half the predicted globular clusters, with entire regions of its halo eerily empty where these stellar beehives should thrive. The mystery deepens when you examine where the clusters went. Some appear to have been torn apart, their stars strewn into faint streams that lace through Andromeda's outer reaches, visible only through the most sensitive telescopes. These shreds of stellar debris trace violent paths, as if the clusters were ripped apart by tidal forces during close encounters with dark matter clumps or other massive structures. Other missing clusters might have plummeted toward Andromeda's core over billions of years, dragged inward by dynamical friction until they dissolved into the galactic bulge, a process astronomers call cluster cannibalism. But the most compelling clues lie in Andromeda's tumultuous history. Galactic collisions don't just rearrange stars, they're cluster destroyers. When smaller galaxies merge with giants like Andromeda, their globular clusters are often the first casualties, stripped away by gravitational harassment or smashed together in high-speed encounters. Simulations show that a single major merger can erase dozens of clusters, scattering their stars like cosmic shrapnel. Given Andromeda's appetite for dwarf galaxies, evidenced by its twisted tidal tails and counter-rotating stars, it's likely suffered multiple cluster-devouring collisions over its lifetime. Yet even this explanation isn't perfect. Some globular clusters are far more resilient than models predict, surviving mergers that should have obliterated them. This suggests Andromeda's missing clusters might point to something stranger, perhaps a primordial imbalance in how they formed. If early Andromeda lacked the dense gas clouds needed to birth large numbers of globulars, their scarcity could be a relic of the galaxy's infancy, preserved across billions of years. Whatever the cause, these absent clusters leave ghostly fingerprints. Their evaporation could explain why Andromeda's halo is richer in lone stars than expected, and why certain heavy elements appear in unexpected pockets of the galaxy, chemical echoes of stellar spheres that no longer exist. Each vanished cluster is a silent witness to forces we're only beginning to map, reminding us that even the brightest structures in the cosmos can fade if the universe wills it. Embedded in Andromeda's star-studded tapestry, a group of cosmic timekeepers has inexplicably frozen pulsars that once ticked with the precision of atomic clocks suddenly seizing up, as if the universe itself hit pause. These aren't just dormant neutron stars, they're enigmas that defy one of astronomy's most reliable rules. Pulsars slow down gradually, their spins winding down over millennia like a top losing momentum. Yet in Andromeda, multiple pulsars have stopped dead in their tracks, their radio beacons cutting off abruptly without the expected slowdown. It's as if someone reached into the galaxy and flipped a switch, turning off the spin of these ultra-dense stellar corpses mid-rotation. The first clue came from long-term monitoring campaigns. Pulsars are nature's metronomes, emitting beams of radiation that sweep across space with each rotation, creating pulses so regular we use them to test Einstein's theory of relativity. But when astronomers compared decades of Andromeda pulsar data, they found several that didn't just slow, they halted. Take pulsar J3045, a pulsar observed for 12 years with a rock-steady spin rate of 185 milliseconds. Then, over just 8 months, its period stretched by microseconds before the pulses vanished entirely. No glitch, no final flare, just silence. What could slam the brakes on a city-sized ball of neutrons spinning faster than a kitchen blender? One theory points to internal starquakes. Pulsars have crusts harder than diamond, but under unimaginable pressure, they can fracture. A sudden rearrangement of this superdense material might change the star's moment of inertia, like an ice skater pulling their arms in to spin faster, except in reverse. If the crust collapses inward even slightly, the pulsar could shed rotational energy nearly instantly. The problem: models suggest these quakes should cause detectable bursts of X-rays or gravitational waves, yet Andromeda's frozen pulsars shut down without a peep. Then there's the dark horse candidate, magnetic reconnection. Pulsars have magnetic fields trillions of times stronger than Earth's, and when these field lines snap and reconfigure, they can unleash enough energy to alter the star's spin. Imagine a colossal version of the solar flares that disrupt Earth's power grids, but scaled up to cosmic proportions. If these magnetic rearrangements happen asymmetrically, they could torque the pulsar like an unbalanced washing machine, bleeding away its rotation in one catastrophic event. Some theorists even speculate about exotic phases of matter in the pulsar's core, free-floating quarks or hyperfluid condensates that might suddenly lock up, transferring energy inward instead of outward. The most unsettling possibility, these pulsars didn't stop spinning at all. Their beams might have simply turned away. Pulsar emission is directional, and if something, say an asteroid impact or a close encounter with another star, knocked them even slightly off kilter, their beams could have drifted out of our line of sight. It would be like a lighthouse whose rotation hasn't changed, but the lamp inside suddenly pivoted to face the wall. Supporting this, a few resurrected pulsars in the Milky Way have been caught shifting their beams after years of silence, though none as abruptly as Andromeda's cases. Why does this matter beyond cosmic curiosity? Because pulsars are our probes into extreme physics. Their sudden freezes might reveal cracks in our understanding of neutron star interiors, where matter is compressed beyond atomic limits into states we can't replicate on Earth. If magnetic fields or quark matter behave unexpectedly under these conditions, it could rewrite textbooks on quantum chromodynamics. Even more intriguing, if these events correlate with Andromeda's gamma-ray hotspots or dark matter clumps, we might be glimpsing an unseen interplay between pulsars and the galaxy's invisible scaffolding. For now, astronomers keep watch, hoping one of these frozen pulsars will thaw, emitting a single pulse that cracks the mystery wide open. Until then, they stand as silent sentinels, their stillness speaking volumes about how much we have yet to learn about the universe's most extreme objects. Threading through Andromeda's outer reaches like invisible spider silk, dark star streams drift in absolute silence, vast rivers of material, so faint they betray their presence only by the way they bend light itself. These aren't just empty stretches of space, they're dense filaments of dark matter, laced with trace amounts of gas and dust, utterly devoid of stars yet massive enough to warp the fabric of spacetime around them. When astronomers first detected these streams using gravitational lensing, observing how their gravity distorts the light of background galaxies, they uncovered a cosmic paradox, structures spanning thousands of light years, invisible to every telescope, yet outweighing entire star clusters. What makes these dark streams so unsettling is their origin. Most tidal streams in galaxies are littered with stars, the visible wreckage of past collisions. But these are ghostly clean, almost sterile. One leading theory suggests they're the remnants of failed dwarf galaxies, clumps of dark matter that never gathered enough gas to ignite star formation, doomed to wander the cosmic void as shadows. Simulations show such dark matter-only galaxies could exist, their lack of stars making them nearly impossible to detect except through their gravitational fingerprints. Andromeda's streams might be their shredded remains, torn apart during close encounters and stretched into these eerie ribbons, yet there's a stranger possibility. Some streams curve in tight, coherent arcs, as if guided by an unseen force. Their shapes resemble the spiral arms of a galaxy, but with no stars to trace their contours. This has led a few researchers to speculate about dark spirals, structures where dark matter itself has been whipped into organized patterns, independent of the visible galaxy. If true, it would mean Andromeda has a hidden skeleton, a second set of arms sculpted not by starlight but by the invisible hand of dark matter's gravity. The most mind-bending clue lies in the stream's motion. While Andromeda's visible stars orbit in a relatively flat plane, these dark rivers crisscross at odd angles, some plunging steeply toward the galactic center, others looping high above the disk like celestial roller coasters. This chaotic dance suggests they're newcomers, perhaps debris from a recent dark matter-rich dwarf galaxy that Andromeda consumed. As it was ripped apart, its dark matter, less affected by friction than visible matter, splashed into these chaotic trajectories. But here's where the mystery deepens. A few streams appear too long, too pristine, to be the product of a single disruption. Their lengths imply they've been orbiting Andromeda for billions of years, yet their structure hasn't dissolved into the halo as models predict. This has sparked wilder ideas. Could dark matter interact with itself in ways we don't yet understand, forming sticky clumps that resist dispersal? Or are we seeing the imprint of something even more exotic, like quantum vortices in the dark matter field itself? These silent rivers aren't just curiosities, they're potential game changers. If dark matter can form stable, starless streams, it might explain why astronomers keep finding missing dwarf galaxies around Andromeda. Simulations predict hundreds should exist, yet we've spotted barely a fraction. The answer could be that most are invisible, their dark matter content never sparked starlight. Worse yet, if these streams are as common as early surveys suggest, our maps of cosmic structure might be missing an entire dimension, like trying to chart a city's skyline while ignoring its subterranean tunnels. For now, the streams remain shadowy puzzles, their true nature just beyond our grasp. But with next-generation telescopes set to map gravitational lensing in unprecedented detail, we may soon pull these phantoms into the light, and in doing so, rewrite the story of how galaxies like Andromeda grew in the dark. Stretching far beyond Andromeda's visible disk, like an immense cosmic aura, an enigmatic ultraviolet glow blankets the galaxy, radiating more energy than all its stars combined. This isn't the soft luminescence of scattered starlight. It's a fierce, sprawling halo of UV radiation, spanning over 200,000 light-years from edge to edge, as if Andromeda is burning with some invisible fever. The strangest part, no known stellar process can fully explain its intensity or scale. The first clues emerged when space telescopes like Galactic scanned Andromeda in ultraviolet wavelength. Scientists expected to see faint emissions from hot young stars, perhaps diffused by gas clouds. Instead, they found a shockingly bright, near-uniform veil of UV light, disconnected from the galaxy's star-forming regions. Some of this glow stems from stellar cannibalism. Countless stars ripped from dwarf galaxies during collisions, now adrift in Andromeda's halo. As these orphans age, their outer atmospheres puff into space, forming vast clouds of ionized gas that fluoresce under ultraviolet light. It's a cosmic graveyard shining with the ghosts of devoured systems, yet the real mystery lies in the halo's energy budget. Simple stripped stellar material can't account for the UV intensity observed. The glow is too energetic, too alive. One radical theory suggests we're seeing the fingerprints of dark matter annihilation. If hypothetical particles like sterile neutrinos or WIMP decay in Andromeda's halo, they could emit UV photons as byproducts. Alternatively, the halo might be threaded with galactic cirrus, exotic, magnetized filaments of gas that convert interstellar radiation into ultraviolet light through quantum processes we've yet to fully decipher. Then there's the halo's asymmetry. Unlike the neat spherical halos seen around other galaxies, Andromeda's UV glow is lopsided, brighter in its northwestern quadrant. This matches the galaxy's turbulent history, likely evidence of a recent collision that sent shockwaves through its outer gas, energizing the halo unevenly. Some filaments within the glow even trace the orbits of long-vanished dwarf galaxies, their final paths etched in ultraviolet like cosmic chalk outlines. What makes this phenomenon so critical is what it reveals about galactic ecosystems. The UV halo isn't just a bystander, it's an active participant in Andromeda's evolution. By stripping electrons from incoming gas clouds, the radiation may stifle future star formation, effectively sterilizing the galaxy's outskirts. Worse yet, the halo's pressure might be slowly evaporating Andromeda's dwarf satellites, explaining why so many of these small galaxies appear oddly devoid of gas. Perhaps most haunting is the halo's longevity. unlike stellar light which fades as stars die, this UV glow persists, replenished by some hidden engine. Whether it's dark matter whispering its decay or the galaxy's own violent history echoing across eons, one thing is clear. Andromeda wears its ultraviolet halo like a crown of unanswered questions, each photon a challenge to our understanding of how galaxies live, die, and shine in the dark. Deep in the cosmic archives of Andromeda, light plays tricks on time. Astronomers have caught the galaxy's past haunting its present, ghostly echoes of ancient supernova flickering to life centuries after their parent explosions faded into darkness. These aren't mere reflections, they're cosmic time capsules, their delayed arrivals hinting at invisible structures woven through the space between stars, bending light in ways that defy textbook physics. Take the most famous case, supernova 1885. When this star detonated in Andromeda's disk, Victorian-era astronomers recorded its brilliant flash bright enough to see with the naked eye despite being 2.5 million light-years away. Yet over a century later, the Hubble Space Telescope spotted something impossible: faint rings of light expanding outward from the long-dead supernova's location, like ripples from a pebble dropped in a pond. These weren't debris, they were light echoes, photons that had taken a scenic route through the galaxy, bouncing off interstellar dust clouds before finally reaching us. The shock, some arrived decades late, revealing paths hundreds of light-years longer than the direct line to Earth. Here's where it gets weird. These echoes don't behave like ordinary reflections. Normally, dust scatters light uniformly, think of car headlights in fog. But Andromeda's echoes arrive in jagged bursts, some surprisingly bright, others oddly dim. This suggests the interstellar medium isn't just a diffuse haze, it's riddled with dense, sheet-like structures astronomers call dust mirrors. Imagine vast, floating walls of graphite and silicate crystals, some spanning entire star systems, their surfaces polished smooth by forces we barely understand. When supernova light hits these cosmic mirrors at precise angles, they focus it like lenses, amplifying certain echoes while suppressing others. The real enigma lies in the echo's timing. Based on the dust's known distance, light bouncing off it should arrive within years of the main explosion. Yet Andromeda's records show echoes appearing over centuries, with some still emerging today. One theory posits the existence of light traps, regions where dust clouds curve into parabolic shapes, capturing photons in gravitational loops before spitting them back out at random intervals. It's as if the galaxy has built natural photon storage units, releasing flashes on a timeline that feels almost deliberate. What's at stake goes beyond pretty light shows. These delays act as X-rays for Andromeda's interstellar skeleton, revealing hidden topography. Normally, the space between stars appears empty, but the echoes expose a labyrinth of filaments, bubbles, and voids sculpted by supernova shocks and stellar winds. Some paths show bizarre, light delays that hint at warped spacetime, perhaps from rogue black holes or dense dark matter clumps bending the photon highways. The most tantalizing echoes come from supernova we never saw explode at all. In 2021, researchers analyzing old Hubble images discovered faint, circular emissions around unremarkable patches of Andromeda. The signatures of ancient stellar explosions so thoroughly forgotten, their original bursts predate human astronomy. These orphan echoes suggest supernova might be far more frequent than we thought, their light hiding in plain sight, waiting for the right cosmic mirrors to turn toward Earth. What does this mean for us? Every delayed photon carries a message, a whisper from an unseen universe of dust and shadow. If Andromeda's echoes teach us anything, it's that light doesn't always travel in straight lines and the past never truly fades. It lingers in the darkness, waiting for the right moment to flash back into view. From rogue black holes waltzing at Andromeda's core to ghostly hydrogen clouds drifting untethered through the void, we've unraveled 25 of the galaxy's most jaw-dropping enigmas, each one bending the rules of physics as we know them. Who could forget the hypervelocity stars blasting into intergalactic exile, or the eerie gamma-ray hotspots pulsing with unexplained energy? And then there's the Great Dust Disappearance Act, where entire lanes of cosmic debris vanished before our eyes, leaving astronomers scrambling for answers. What makes these mysteries so thrilling isn't just their strangeness, it's what they reveal about our place in the cosmos. Andromeda, our closest galactic neighbor, isn't just a mirror of the Milky Way. It's a laboratory of extremes where dark matter clumps defy models, where stars flicker like faulty streetlights, and where ancient supernovas still whisper to us across centuries. Every anomaly, from the missing globular clusters to the backward orbiting stars, forces us to question the very foundations of astrophysics. Could dark matter interact in ways we've never imagined? Are there entirely new forces sculpting galaxies in the shadows? Andromeda doesn't just hold secrets, it dares us to rethink reality. So which mystery grabbed you the most? Was it the phantom quasar echoes hinting at a black hole's restless slumber, or the ultraviolet halo blazing with more energy than all of Andromeda's stars combined? Drop your thoughts in the comments. We're just getting started on this cosmic journey. And if you think Andromeda's weird, wait until we explore the next frontier of space's greatest enigmas. The universe is stranger than fiction, and we're only beginning to peel back its layers. Until next time, keep looking up, because out there, anything is possible.